All right, so tonight we're going to look at some inverse functions. Then we're going to look at exponential graph equations. We're going to look at graphing them and solving some of them. And we're going to end up with the beginnings of logarithmic functions. We're going to get into a lot more logarithms on Wednesday's class. So the first thing we're going to look at is basically how we determine if a function can have an inverse. So a function is, we looked at it before, that's the vertical line test. So the first one up here is a function. This one's a function. Actually, I think all these actually end up being functions. So they all pass the vertical line test. So to determine if they have an inverse, they actually have to pass the horizontal line test because we want a one-to-one relationship. So if a function can pass the vertical line test, that means not only does the domain, every piece in the domain only have one answer in the range, every piece in the range only has one answer in the domain. So when we go up on this one fails that because at this point, there's two ranges that are the same. So this would be a no, it's not a one-to-one relationship. Same thing on this one. So we have two domains that gives us the same range. So that would also be no, not a one-to-one relationship. This one, same thing. This is a sine function, and it also fails the one-to-one test. Look here, that's 1, 1, 1, 1, 1, 1. So every output and input, it's a one-to-one relationship. So that's a yes. That is this one, linear. Linear function is a one-to-one relationship. And then even though this is a piecewise, right there we have an open dot and a closed dot, that's fine. So yes, that is a one-to-one relationship there as well. So this topic is called the horizontal line test, and that's all you're doing. You're basically just taking it and doing just like the vertical line, except you're doing it as a horizontal line. And you're trying to determine if there actually is a one-to-one relationship, which means that I can find an inverse for the original function, which is what now we're going to do. So this one, so in this topic right here, we actually want to determine if they are inverses of each other. So the first function we're looking at, we have f of x is x plus 3, and g of x is x minus 3. So they're doing those composite functions that we were doing before. So we're going to do f of g of x first. So that means f of x minus 3. So I'm going to do x minus 3 plus 3, which equals x. So that one is x. Now we have to do the g composed of f of x. So we've got g with the x plus 3 on the inside. So we got x plus 3 minus 3, which turns out to be, again, just x. As long as they both come out to be x, they have to be exactly x, nothing else, no negatives, not the same, they both have to be exactly x. Then they're inverses of each other. If they do not come out to be both exactly x, they are not inverses of each other. Yeah, so I'm going to actually do B, it's the same thing too. But basically, you're plugging in the values, just like we did with the composite functions last week. And you're solving them, you're simplifying them down. So the goal is, if they're inverses of each other, they both should come out to be x's. And in this case, they do. So that's why they're inverses of each other. I'm going to do the same thing for this one. So if it's the plugging in part, I'll do that on this one here. So let's look at, actually, we'll do this one. So I've got f of x is 1 over 2x, and g of x is negative 1 over 2x. So I'm going to do the f g of x. So I'm going to do f, and actually I'm going to change the colors to make this a little easier to see. And I'm going to plug in negative 1 over 2x. So I have 1 over 2 negative 1 over 2x. So we're plugging it in to where that part is. So now, when I simplify this down, I get 1 over negative 1 over x, which ends up giving me just negative x. So this first one is negative x. Does that make sense now? All right. So then we're going to do the other one too. We're going to do the g of f of x. So I do g, and then I'm going to plug in 1 over 2x. So it equals 1 over 2 and then 1 over 2x. Oh, I forgot the negative sign in front. So I get negative 1 over x, which equals negative x. So these both come out to be negative x. So they both come out to be the same, but they're not both exactly x. No negatives or anything else. So they are not inverses of each other. The inverse would have gotten rid of the negative sign as well. So they both have to be x's for it to be inverses. If it's anything else, even if they're the same, it is not inverses of each other. Right. All right. So in this topic, the number, when you have the negative 1 up top, it's looking at it as an inverse. So this is the inverse of g of x. So this right here, that's g of x. So if I'm looking for the inverse of it, so in this case, actually, it's not g of x. It's g of 8. So when I'm looking for the inverse, typically it's g of x equals y. If it's the inverse, it's g of y equals x. Because the inverse reverses the domain and the range. So I'm plugging something in from the range and I'm getting something in the domain, unlike we were doing before. So in this case, where it says the inverse of g of is 8, I'm looking at my y values. So we're looking right there. So the answer is negative 1 because it's that's the y and I want the x value as my answer. So if I was to ask for g of 5, the inverse of g of 5, the answer would be negative 8. Because again, you're looking at the y and you're going to give me the answer as the x. All right. Next one. So h negative 1 of x is what we're looking for. They give me h of x. They tell me h of x is 3x plus 13. Now remember, when we're doing the inverse, things reverse. So this is y equals 3x plus 13. If I'm doing the inverse, I'm going to reverse those two. So instead of doing that, I'm going to actually, it's x equals 3y plus 13. Now, I can't leave it like that. I have to solve it for y again, just like we solved the other equations. So subtract the 13. So I get x minus 13 equals 3y and divide by 3. So x minus 13 divided by 3 equals y. So that is my inverse. X minus 13 divided by 3. So when we're doing this one, we want to reverse the number, reverse the x and the y, and then resolve it for y, or for the y. Now, in the last question, I said that if they're inverses of each other, which is what we just did here, if I plugged it back in, I should get exactly what x is. So that's what I should get. So since that rule holds true, if I'm going to do the inverse of each other, this answer here is always going to be whatever answer they ask for. So in this answer, it's going to be negative 8. If they said 5 there, I'd have put 5. If they said 3, I'd have put 3. Doesn't make a difference which number they put there, that's going to be the answer there. I'm going to do one more of these. Just want to make sure you guys get the concept of the switching and stuff. Just trying to see if they'll give me one that doesn't have a straightforward linear equation. Nope, and they're all going to be the same. Okay. All right, so the first one, the g negative 1 of 9. So again, I'm looking for the 9 and the y, which is there. So then my answer is negative 5. Now I'm looking for h negative 1 of x. So h of x is 9x minus 8. So it's y equals 9x minus 8. So we're going to switch. And then we're going to resolve. And so it's x plus 8 divided by 9 equals y. And that's h negative 1 of x. So we got x plus 8 divided by 9. And now this one, the number inside here is a 1. So the answer is a 1. All right. This one's very similar to what we just did. Again, we're going to sit there and we're going to reverse the x and the y. So, except the problem's a little more complicated. So again, we're going to do the y equals. We're going to switch the x and the y. And now we're going to resolve. Now I'm going to square. Bring the 4 over. And switch all my signs. So there's my inverse. So it's 4 minus x minus 7 squared. The next thing it wants to know is our domain. Now, if you look at just this equation right here, there is no domain restrictions. There's no square roots. There's no division by 0. So you might think the domain is all real numbers. But you got to remember, this is an inverse of another function. So when we're looking at the inverse of a function, the domain and the range switch. So the domain of the inverse is the range of the original function. So if we're looking at this function right here, so if we're putting in the f of x equals the square root of 4 minus x plus 7, the domain was negative infinity to 4. So if I plugged in the smallest number that could possibly exist in this problem is 4. I mean, when I plug it in, if I plug in the 4 here, the square root goes away, and all I'm left is the 7. So if I plug in, so the first number is 4, 7. If I plug in infinity to this, the square root goes to infinity. So that means it goes to infinity. So the next point would be, if I plugged in negative infinity, it would be infinity. So my range of this function is 7 to infinity. Those are the numbers that I can get out of this problem. The smallest number I could get out is 7, and then I would get all the numbers all the way up through infinity. Since that's my range of that function, when I go over to my inverse function here, that becomes my domain of my inverse function. So my domain is 7 to infinity. Does that make sense to everybody?
I have a quick question.
Sure.
If the domain is 7, but you plug 7, never mind. I'm plugging 7 into the inverse and it works. Never mind.
Okay. So, all right, let me go through the domain and the range part of it again. Actually, I'm going to show this a little bit of a different way. It might make a little more sense. Not the whole screen yet. All right. Square roots, 4 minus x plus 7. All right, so if we look at this graph, so my domain for this function goes from negative infinity. So my domain is from negative infinity all the way to 4. So negative infinity to 4. That's my domain. My range of this function, if I look at it, goes from 7 all the way up to infinity because it keeps going. So my range is 7 to infinity. So when I'm doing the inverse of it, the range and the domain switch. So the inverse of this function, this is my range, is in this, it now becomes my domain of my inverse function, because the inverse function switches the x and the y. So it switches the range and the domain. Does that make sense now? Let's see something real quick. One second, I'm just trying to see. No, so you're not going to have to graph it to do it. The easiest way to do it is how I did it before, by just plugging in the values in. I want to actually show you the inverse of this. 4 minus 7 minus squared. And I put in oh. All right.
I did have another question.
Sure.
So, like, pretend our original function was something like x squared, where the inverse would be like the root, right? Now, when you're writing the domain for the inverse, and obviously the range for the original function would have been all real numbers. Does that is there any exclusions now in the domain of the inverse?
If the domain of the range, or so if the range of the original function was all real numbers, then the domain of the inverse will be all real numbers. There will be no restrictions.
Okay.
Because
even if I have to square root a negative number.
Well, there's a very possible. Not every function has an inverse. So a parabola, for example, doesn't have an inverse because it fails the horizontal line test.
Aha. Okay.
So you can't get the when you were looking at that concept, it was like taking like y equals x squared. There is no inverse of y equals x squared because it fails the horizontal line test.
Oh, I see. So, I mean, so the inverse wouldn't exist, and then domain
correct
also. Okay.
Yeah,
got it.
The inverse wouldn't exist at all. So honestly, the easiest way to do this is actually not to graph it. The graphing is a nice way to look at it, but the easiest way to do it is actually figure out what the range is of the original function by plugging in your domain. So that's kind of what I did here. I took my domain, I plugged in negative infinity to the problem. If I plug in negative infinity to it, I'm going to get out infinity. So that's that value. If I plug in 4 to this problem, I'm going to get out 7. since 7 is the smallest number that I can get out, that's where I started my range. So it's going from 7 to infinity. So that becomes my domain. So originally I didn't do it with the graph. I was using the graph to kind of just to show you an easier way to, a graphic way to look at it. So you can see where I got the 7 to infinity from. But honestly, just plugging the values in would be the actual fastest way to do it. All right, let me do one more of these so you can see it. And see if they give us one more. It's probably going to be the exact same thing anyway. Oh, actually, it's slightly different. All right, so we're going to take my original function and we're going to find the inverse of it. So I've got y equals 3x minus 9. So x equals square root of 3y minus 9. So I have to square it first. So I got x squared equals 3y minus 9. So x squared plus 9 equals 3y. So x squared plus 9 divided by 3 equals y. So that's going to be my that's going to be my inverse function. Now, if you listen to what I said a minute ago, I said you do not, a parabola does not have an inverse. And that's true. So how can a parabola be an inverse of a function? And it's because of the domain restriction. So when I'm taking a function like this and I'm making up this one, which is now basically a parabola, I'm going to have a domain restriction that eliminates all the values that would have given me my negative square roots the other direction. So we have to figure out my range of my original function. So I have y equals the square root of 3x minus 9. If I plug in 3, so this is my domain, and that's my range. If I plug in 3, I'm going to get 0. If I plug in infinity, I'm going to get infinity. So my new range, my range of my original function is 0 to infinity. So my domain of my new function is 0 to infinity. And if you were to graph this parabola, its vertex is at 0. So you're only looking at the right side of that parabola. You don't have the left side of it, which then works with the vertical line test. All right. Let's move on to the next one. All right, so very similar concept. We have to find the inverse of it, except this one's got 2 x's, which makes life a little more complicated. So we've got y equals 9x over 7x minus 5. So I've got x equals 9y over 7y minus 5. So now I'm going to get rid of the bottom. So I have 7xy minus 5x equals 9y. I'm going to move my y's over to one side. So I have 7yx minus 9y equals 5x. I'm going to pull out the y. So I have 7x minus 9 equals 5x. And then I'm going to divide by to 7x minus 9. So that is my inverse. So the key piece when you're doing, when you have multiple x's or multiple y's, when you actually have to resolve it, is to get all the y's on one side, all the x's to the other side, and then basically you can factor out the y, and then you're going to be left with just the x's and stuff that you can divide off. All right, So now we have to look at my original function because we need my domain and my range. So if we look at the original function, so actually, hold on, let's do the inverse first. Let's find the domain of this one. So the domain of this one, of my inverse, is just where the bottom, so 7x minus 9 cannot equal 0. So that means 7x cannot equal 9 and x cannot equal 9 over 7. So that's the domain of my inverse. Now, there's a reason why I didn't find the range of my original function first. It's harder. You could find the range of that one. It's just a lot more complicated to do because you're not looking for like beginning and end values. You're looking for a whole, and that makes your life a little bit more complicated to do it. So it's easier just to do it this way. So you're doing negative infinity to 9/7, and then union 9/7 to infinity. Now, the range of your inverse, based on what we've been talking about, is the domain of my original function. So instead of going back and trying to find the range of this function here, I can just find the domain of my original function. So again, all I really have to look at is the bottom. So 7x minus 5 cannot equal 0. So x cannot equal 5/7. And that's my domain of my original function and the range of my inverse because they switch directions. So I'm actually going to copy paste this, just change the number. So don't try to find the range. So if you don't have to find the range, don't find the range. Find the domain and then flip it. Makes your life a lot easier. Honestly, for most situations, finding your range is actually kind of difficult, and you might have to use the graph. The last topic we looked at, the way that question is designed, it makes the finding the range really easily. All right, any other questions on inverse functions before we move on to exponential functions? All right, exponential functions. So most of the function that we've looked at so far, the x has been in the base or inside parentheses or square roots. Exponential functions, the x is in the exponent. So when we're looking at this one, where we have 7 to the x power, we're plugging the values into the x. So we've got -2, -1, 0, 1, and 2. I'm going to go backwards just because I want to make sure you actually see something. So 7 to the second power is 7 squared, which is 49. 7 to the first power is 7. What's 7 to the 0 power? Anybody?
1.
Very good. 7 to the 0 power is 1. 7, anything to the 0 power is always 1. Do not put 0. Now, when we get to the negative ones, if you notice, we're dividing. So the negative ones are not negative values. They're fractions. So this becomes 1/7 and 1/49. So remember your exponent rules. Otherwise, you're going to be in for a world of hurt doing these problems. So 1/49, 7, 1, 7, and 49. All right, I'm not going to do another one of those because I think everybody kind of got that concept, and we're going to use it in the few problems in a minute anyway. All right, this is one of those ones that look really, really complicated. It's really simple. All you're doing is plugging the values into it. So current price is where it's 0. So I would just use the calculator. You actually can type the entire problem right into the calculator. 1.041. And then raised. And the current price is 0. So you get 2,500. Price 9 years from now, just hit undo and change the 0 to a 9. And round to the nearest, it says round to the nearest dollar. So 3,589. All right, next one. This is the same thing. The only difference is they don't give you the equation. So you have to write the equation. The function for compound interest is A equals P, 1 plus R over N to the NT. So P is your principal. It's your starting value. R is your rate. And that's always as a decimal. T is time, typically in years, although it doesn't always have to be. And N is the number of periods. So N is how many times is compounding. So annual is 1, semi-annual is 2, monthly is 12. And I think that's actually the only ones you see in this problem. So depending on the bank, daily is actually 360 and not 365. So all right, so we're going to plug in our numbers to this problem. So my original amount was 41,000. Do 1 plus. My interest rate's 0.055. It's an annual interest rate, so, or annually compounding, so that's 1. And then we're raising it to, we're doing 9 years, so 9 times 1. So they get, and they want this to the nearest dollar, so $66,383. All right. Any questions with those? Those should go pretty quick. Now that you know the formula, if you didn't remember it, those questions should go pretty quick. All right, let's start looking at graphs of exponential functions. So the first question, the first topic we're going to look at is looking at domain and range of the function. If we're looking at this exponential function, you notice a dashed line down here. That dashed line is known as an asymptote. The asymptote is a line where the graph gets really, really close to, but does not touch. So in this case, my domain, let's look at the domain, is all real numbers. It's going from negative infinity to positive infinity. So my domain is all real numbers. In an exponential function, your domain, unless there's other restrictions on it, will always be all real numbers because any number can be plugged into the x value. Your range, however, is not. Your range is dictated by where that asymptote is. So in this case, my range is goes from -4 to infinity, but it's going to be greater than that. So y is greater than -4, not equal to, because it never actually touches -4. So your domain is all real numbers. Your range is y is greater than -4. All right, let's do one more of those. All right, same thing here. My domain, again, is all real numbers. Even though this graph looks like it goes through the dashed line, it's a figment of the actual equation on the screen. It does not actually cross that dashed line. So my range, in this case, is from negative infinity to negative 1. So that means y is going to be less than negative 1. So just be careful when you look at this. Say, oh, it looks like it touches the line. An exponential function will never touch the asymptote. Questions with that? Hold on a second. Okay. All right. Move it along. All right, so now we have to graph the exponential function. To graph an exponential function, they want 5 points in the asymptote. So when you're graphing your function, the easiest way to graph it is to use -2, -1, 0, 1, and 2. So the first thing we're going to do is we're always going to start off with that parent function. So basically, we're going to start off with those 5 numbers. And in the next couple of topics we're going to look at, we're going to do transformations to them to get my values. Kind of like what we did when we graphed the square root functions and stuff before. We graphed the base one, and then we did the transformations off of that. So it's 5 over 2 to the second power, which is 25 over 4. 5 over 2. 0 is still 1. And then these flip it over. So it's 2 over 5 and 4 over 25. When you're graphing it, take those 5 points. Now, I would suggest not trying to use the pencil. Type the numbers in, especially considering we have fractions. And don't ever try to do these as decimals. Always leave them as fractions. All right. Your asymptote line is going to be whatever is added to this function here. So see how there's nothing added to it? So my asymptote line is 0. And then we graph my equation. If you messed up a point, let's say we messed up one of our points. Let's say we did 20 over 4 instead. Now we plotted our asymptote and we graphed it. You're going to get something a little crazy. If you get something crazy like that, you probably made a mistake. Go back and look at your points. So you're going to get a nice curve when you do this. Otherwise, you made a mistake. And for exponential functions, you're always going to have a horizontal asymptote. All right. This is where I was talking about we're going to start looking at the transformations instead of sitting there doing out all the problem every time. So in this first problem, what I'm going to do is I'm only going to worry about the 4x. So I'm going to graph my equation, do my points the same way I did with the other ones. -2, -1, 0, 1, and 2. So I'm only going to do it with the 4x. So it's 16, 4, 1, 1/4, and 1/16. Now I have a 1/4 outside. Now that 1/4 is outside of the parentheses. So I'm going to multiply the y's by 1/4. So it's 1/4 y. So that gives me 1/64, 1/16, 1/4, 1, and 4. So instead of going through and doing every problem out by plugging the number in and then multiplying it by 1/4, do the 4x, which you can do pretty easy and in your head, and then multiply it by that 1/4. And now we're going to graph those points. So it's going to be -2 and 1/64, -1 and 1/16, 0 and 1/4, 1, 1, and 2. Now, my asymptote, notice how, again, there's nothing added to this. So my asymptote is still at 0. And we get our nice little curve there. Questions on that one? We're going to do a couple more of them too. So. All right. Same thing. So I'm going to do my xy, -2, -1, 0, 1, and 2. We're doing it on just the 4x. So 16, 4, 1, 1/4, and 1/16. Now it says +3. So I'm going to add 3 to all these. So the ones down here are really easy to add 3 to. And I'm going to show you a nice little trick. So this one, on this topic, you actually don't need that many points. So when you're graphing it, it wants you to graph the horizontal asymptote. Now notice, this one, I have a +3. So I'm going to graph it at 3. It wants me to plot, it only needs 2 points. So I'm going to plot 0, 4 and 1, 7 to get your graph. So for this topic, since it doesn't say 5 points, you only need 2 points to graph it. I wanted to get in the habit of doing those. And the other thing I'll show you, and actually why I wanted to show you this, is that you can actually plot the points. If we do 1/4, you can put +3 right in the point, and it will actually graph that point as 1/4 +3. So you don't actually have to sit there and do out the calculation to plot the points in the actual plot tool, which makes your life a lot easier. All right, so my domain for a rational function or an exponential function is all real numbers. So now they want this in interval notation. So it's -infinity to infinity. My range starts at 3 and goes to infinity, but it doesn't hit the 3. So 3 to infinity. So just little things to help you when you're doing these topics. Questions on that one? All right. A couple more exponential ones. All right, so now this one, they're already giving you the graph and they want you to do the transformations to the new function. So if we look at my function, so they graphed the original one. They graphed y equals e to the x. And we want to do the transformations to get it to y equals e to the -x minus 5. So this negative sign switches my x's. So that means I'm going to invert it over the y-axis, because that means my x values change. So if it's a negative next to the x, you're inverting it over the y-axis. If it's outside, it's flipping over the x-axis. This -5 takes the graph and shifts the asymptote down to -5. So not the point, the asymptote goes down to -5. My domain, again, all real numbers. My range, -5 to infinity. Let's try one more of those. All right. So now this one, we've got y equals -e to the x minus 2. So my transformation in my x is subtracting 2. So remember, we're doing the opposite of that. So since it says -2, I'm going to move it +2. So take the point and move it over 2. Now the negative is on the outside, so that's the y. So that means it's flipping over the x-axis. So remember, whatever's next to the x, you're doing the opposite of what it says. And then outside, you're doing it to the y value. So again, domain, all real numbers. Now my range is going from -infinity to 0 in this one, because I didn't move my asymptote at all. Any questions on that one? All right. So let's take this equation. So we've got y equals 2e to the x minus 3 minus 3. I only need 2 points in the asymptote. So I don't really need to do a ton of problems. I can just do the 0 and the 1. So 0 for e is 1, and 1 is e. Now, let's look at my transformations. So the first one, we're going to do this piece up here. So it's x minus 3. So that means I'm going to add 3 to the x's. So that's 3, and that becomes 4. Now we're going to do the 2 and the -3 to the y. So I'm going to multiply it by 2 and then subtract 3. So this 1 becomes -1. And this e becomes 2e minus 3. And the asymptote is always what's added to the problem at the end. So that is my asymptote. So in this case, it's -3 is my asymptote. So we're going to graph the asymptote at -3. And I'm going to plot my 2 points. So it's 3, -1. And then 4. And then 2e minus 3. And draw your line. Yes, I will do this one again. So it's all right. So e is not a variable. E is like pi. So e to the x. So if I did that, anything to the 0 power, so e to the 0 power is 1. And if I did 1, e to the first power is just e. So that's where I got those. It's no different than if I did 4 to the x power, it'd be 1 and 4. So e is just like pi. It's a rational number. So you start off with that, and then you do your transformations to it. Let's do one more of those. Not continue. Try another one. All right, so again, I'm going to do my e to the x first. So 0 and 1 is 1 and e. And the one I'm doing right now or the one I just went from? So yeah, so that's where so if you notice, the actual point that I graphed was 3, -1. So it was actually the 3 one was going to give me that 1 value. And the 4 value is actually going to give me the e. So yeah, that's the change. So you do the parent function, then you do the transformations to it. So in this one, my transformations, I have the -4 on the x. So I'm going to do x plus 4. So that's 4, and that's 5. And then this side, I'm going to do 3y minus 4. So this ends up being -1. And this one ends up being 3e minus 4. Now my asymptote in this case is -4 because it's the one at the end. So now I'm going to plot my 2 points. So 4, -1, and 5, 3e minus 4. And graph. This works actually for any of them. It doesn't even have to be an e. If this was 3 to the x minus 4, it'd be the exact same thing. You do the exact same steps when you're doing the transformations. All right. The last 4 topics we're going to look at is the beginning of logarithms, because we started this lesson today looking at inverses or the inverse functions. So exponential functions has an inverse function. It's a logarithm. That's where your logarithms come in. It allows you to take an exponential function and solve it. So the first thing we're going to look at is how we actually get to that point, and then we're going to look at some of the basic exponential or logarithmic functions. So this one, I have 27 equals 9 -x minus 5. Sometimes when we're looking at these problems, it's really easy to change the numbers so that the bases are the same. So I'm going to change this to 3 to the 3rd power. And I'm going to change this side to 3 to 2 times -x minus 5. So 3 to the 3rd power is 27, 3 to the 2nd power is the 9, and then that was already up there. Since the bases are the same, I can make the tops the same. So the equation I'm going to solve to figure this out is 3 equals 2 times -x minus 5. So what we're actually doing to solve this is you're actually doing the log of both sides. But we'll see that a little bit later. So I got 3 equals -2x minus 10. So I've got 13 equals -2x. So -13 over 2 equals x. And that's my answer. So the only way this works is if I can take the 2 bases and turn them into both the same. So the 27 and the 9 are both multiples of 3. So I was able to break it down into the 3's. If it was 24 and 9, I wouldn't have been able to do this. I would have had to do it a different way and using logarithms to solve it. All right, let's try one more of those. So we've got 4 negative x minus 1 equals 8. So I'm going to break it down into 2's and 2 to the third power. So I've got negative 2x minus 2 equals 3. Negative 2x equals 5, and x equals negative 5 over 2. So same thing, break it down to the same basis, and then take the exponents and just solve the exponents. All right. So an exponential function looks like this. So we have b to the x equals y. A log reverses those. So a log, so it's log base b of y equals x. So the base becomes the base of the logarithm, and the x and the y switches places. So log 381 equals 4 goes to 3 to the fourth power equals 81, which completely and utterly makes sense because 3 to the fourth power is definitely 81. If I did 8 to the negative 1 equals 1/8, that's log 8 of 1/8 equals negative 1. So it's basically just looking at it and how I can reverse it. The reason we want to do this is sometimes it's going to be easier for me to solve an exponential function or an exponential equation to find the answer than the log, or vice versa. Sometimes it's easier to find the log value, especially when we're using the calculators to do it. So the first one's 3 to the fourth equals 81. And then log base 8 of 1/8 equals negative 1. Just like we were looking at before, E, so log base E is ln. That stands for natural log. So the log base E is just ln. So when you see an E, it reverses to that. So you don't have to actually put log E, you just put the ln value. So E to the 5 equals x goes to ln of x equals 5. Because that right there is no different than saying log base E. ln of 3 equals y goes to e to the y equals 3. Because again, we reverse the two values. So this one is ln of x equals 5. And this one is e to the y equals 3. All right, last one. So if I was going to ask you what's the log base 5 of 5, most of you probably couldn't come up with that off the top of your head. However, if I asked you 5 to the y power equals 5, what's y going to be? Pretty much all of you would tell me, well, y has to be 1. Because it's really simple when we look at it in terms of an exponential function. That's why changing it back and forth is very helpful. Both of these y equals 1. This one's just obvious to see. Same thing in the next one. If we look at log 2 of 1 over 32 equals y, that might not be easy to figure out. But 2 to the y power equals 1 over 32 is a little easier to figure out. Maybe not as obvious as the first one, but definitely a little easier to figure out. This one, you have to know that it's going to be a negative because it switches over. So I know it's going to be negative because it flips over to a fraction. Now 2 to what power is going to give you 32? And it comes out to be 5. So you have to remember that the fractions are always going to be negative values. So the first one's 1, and this one's negative 5. Let's do one more of those. So we've got log 6 of 1/36. So 6 to the y equals 1 over 36. It's a fraction, so it's negative, and 6 to the second power is going to give me 36. Log 4 to 64. So 4 to the y equals 64. Not a fraction, so 4 to the third power is going to give you 64. And that's it. Any questions? All right, stop the recording.